Hello everybody. In this video we're going to talk about chapter 6, valence bonding theory. Well, there will be just one video in this chapter. Before we talk about the valence bond theories, let's do a quick review about electron groups and electronic configuration. How do we define electron group? Well, let's use ammonia as an example. Okay, here this is the loose structure with its three-dimensional geometry of ammonia and H3. Okay, well, we know that the name of the molecular geometry is trigonal pyramidal geometry. And when we talk about electron groups of central nitrogen, we said that there are 4 electron groups for nitrogen, 3 NH bonds and 1 lone pair. In other words, when we consider the number of electron groups, we need to consider both chemical bonds and lone pairs. Okay, so that's the electron groups. Second thing, electronic configuration. And when we talk about the atomic orbitals, okay, from 1s, for instance, then 2s, to 2p, and then 3s, and 3p. Okay, so this is what we discussed before, and we'll put the electrons here. Then this is going to be hydrogen, 1s1 for hydrogen, okay, and then for helium, then it's going to be 1s2, okay. All right. We will talk about later on when we discuss the hybridization. We need to be familiar with the electronic configuration of some central atoms like carbon, nitrogen. Anyway, so for the first 20 elements in the periodic table, the electronic configuration is required. Okay, here I give you 2 examples, but hopefully this will refresh your memory about what we discussed in this electronic configuration topic. All right. Now let's take a look at valence bond theory. Valence bond theory is a theory that is used to explain why a central atom can form a certain amount of bonds with surrounding atoms. Okay, sometimes you have lone pair on this on the central atom, but it can explain geometries and molecular shape for some molecules. Valence bond theory has its limits, okay, but sometimes it can be used to explain some very basic features of molecules. And actually it worked quite well for those molecules. So let's take a look at this theory, and it's quite easy to understand. Okay, so let's take a look at this example, CH4. We know that CH4 methane molecule. Okay, for carbon, electronic configuration is the full electronic configuration is 1s2, 2s2, and 2p2. Okay, so this is the electronic configuration of carbon. Hydrogen, the electronic configuration is just 1s1. All right, and for carbon, the valence electrons would be 2s2, 2p2, 4 electrons. Okay, so you have 4 CH bonds in this molecule. It's because you have 4 valence electrons, and you use these 4 electrons to share to interact with the electrons from hydrogen to form a 4 CH single bonds. But if you take a look at this picture, we know that when you have electrons on the p orbital, here this is the red bubbles. These are the p electrons. Okay, when those p electrons interacting with hydrogen, okay, for instance this hydrogen, and another p orbital on another p electron on this p orbital interact with this hydrogen, that will give you a bond angle of 90 degree. Okay, in other words, between the 2 neighboring CH bonds, it's going to be 90 degree. However, we know that the CH4 The bond angle is not 90, it's 109.5. So how do we explain this? Well, the valence bond theory can help us. Okay, can help us why the bond angle of CH4 is 109.5 instead of 90. Well, what happened here is, in valence bond theory, this is a standard p orbital, but in valence bond theory, instead of using p orbital to interact with hydrogen, carbon atom will use a hybrid orbital to interact with hydrogens. Okay, so that's why it forms this tetrahedral geometry. It might be a little bit confusing. That's okay. Let's go to next slide, and it will show you some details. Well, here, this is a carbon, electronic configuration of carbon 2s2, 2p2. There's an empty 2p orbital for carbon. Well, a moment ago, we said that if you have these two electrons on the 2p orbital interact with the two hydrogens, the bond angle would be 90, but instead it's not. It's 90, it's 109.5. So how do we explain this? Well, what happened here is, in valence bond theory, these four electrons, okay, they are going to hybrid to generate four orbitals that have the same energy. In other words, those four orbitals, they are going to be on the same energy level. Can you see the difference between this one and this diagram? Well, in this diagram, you see the 2s orbital would have lower energy than the 2p orbital, right? And this 2p orbital is empty. But after these two sets of orbitals form the hybrid orbitals, all four of them will have the same energy, and these four electrons, those four valence electrons on the carbon, will occupy four different hybrid orbitals with the same spin quantum numbers, positive half. Okay, now you can see that since we have four identical hybrid orbitals, when you use those electrons on those four orbitals to interact with hydrogens, all four bonds will be identical. Okay, will be identical. And here, this is the regular s orbital and the three 2p orbitals. And after hybridization, you have four identical hybrid orbitals. And when those four electrons on the four hybrid orbitals interacting with the four hydrogens, they will form tetrahedral geometry. Okay, and since this hybridization involves four orbitals from 2s and 2p orbitals, you can see 1s and 3p orbitals, so we call it Sp3 hybridization. Okay, so S is for the 2s, and P here means the p orbital. 3 tells you how many p orbitals are involved in this hybridization. Since you have three orbitals, p orbitals involved, therefore the number here should be 3. This is a Sp3 hybridization to explain why the bond angle is 109.5 for methane molecule. Okay, another example about how Sp3 hybridization is NH3. Okay, now if you are talking about the nitrogen, the electronic configuration would be 1s2 and 2s2. This is 2p and 2p3. Okay, now when this central nitrogen interacting with three hydrogens, again, these four orbitals from 2s and 2p will hybrid to form hybridization orbitals. In other words, 1s will stay the same, but for 2s and 2p orbital, they'll form four identical orbitals. Okay, and now you have 5 electrons right? So what happened here is you are going to put those 5 valence electrons from nitrogen on those 4 identical orbitals. One is fully occupied, the other 3 remains as singularly occupied. Okay, and when nitrogen interacts with 3 hydrogens, so these 3 electrons will be shared by an H pair. Of course, you know, you have electrons from hydrogen also. Okay, so but anyways, since this is the hybridization among 2s and 2p orbitals, okay, we also call it a sp3 hybridization. Okay, in other words, how do we identify whether a central atom has sp3 hybridization or not? You just need to take a look at the electron groups of the central atom. Okay, if the central atom has 4 electron groups, then the hybridization of the central atom should be sp3. Remember, we drew the structure of ammonia a moment ago. Okay, so we said that since it has 4 electron groups, and that matches with the 4 hybridization orbital here. So it is sp3 hybridization. All right. Now let's take a look at the sp2 hybridization. Well, here you have 2s and 2p orbitals. If you have these 3 orbitals mixed together to generate 3 equivalent atomic orbitals, we call it 3 sp2 hybridization orbitals. S again represents the 2s orbital, and the p 2p, and this superscript 2 means you have 2 2p orbitals get involved in this hybrid orbitals. Okay, here this diagram shows you before the hybridization, and this diagram shows you after hybridization. Okay, one good example of sp2 hybridization is BF3. Okay, we know for boron center, it has 1s2, and okay, and then you have 2s2. Okay, let me write this one here. This is 1s, and this is 2s. And on 2p, you have 1 electron. Okay, 2p here. And when boron center, this is boron center electronic configuration. When boron center interacting with 3 fluorine atoms, these 2s orbital and 2 of the 2p orbital will mix to form 1s. This is a sp2 hybridization orbital, and then you still have 1 2p orbital left. All right, so you have 1s fully occupied, and then you have 3 electrons on this 3 sp2 hybridization orbital. Okay, so those 3 electrons will interact with electrons from the 3 fluorine atoms to form 3 boron fluoride bonds. Okay, all right, and again you can see that, you know, those 3 bonds, they are identical, bond angle 120, and this can be well explained by the 3 identical sp3 orbitals. If they are identical, then you will form 3 identical bonds. Okay, this is a BF3. Now, like sp3 hybridization corresponds to 4 electron groups, sp2 hybridization corresponds to 3 electron groups. Okay, here the BF3, you have 3 electron groups on the central boron center, so 3 electron groups. That tells us this is going to be sp2 hybridization. All right, so this is the first type of sp2 hybridization. You have three equivalent single bonds. Okay, let's take a look at the second type of sp2 hybridization. Before we talk about this specific molecule, let's introduce sigma bond and pi bond. What's the difference between the two? Well, sigma bond means the two orbitals interacting with each other through head-to-head interaction. Okay, usually they will form single bond. Okay, single bond. In other words, if you have one single bond, so that means it's going to be a sigma bond. Now, pi bond, well, you have a p orbital here, second p orbital. When those two p orbitals interacting with each other through side-by-side interaction, sometimes shoulder-to-shoulder interaction, you can see this bubble interact with this bubble and this bubble interact with this bubble. So four bubbles are going to interact with each other at the same time, but in sigma bond, only two bubbles will interact with each other. Okay. Now, this type of side-by-side interaction is called the pi bond. Okay. And this can be observed in double bond or triple bond. Okay. All right. Now let's take a look at this specific example. You have two CH single bonds and one CO double bond. Okay. Let's take a look at this diagram here. This diagram shows us you have these two identical CH bond. This is the head-to-head interaction. Can you see this 1s orbital interacting with this hybrid sp2 orbital through head-to-head interaction? This 1s orbital interact with this sp2 hybridization orbital through head-to-head interaction. Okay, so these are sigma bond. Okay, so if you want to let me to label this is going to be sigma bond. Now, interesting thing about this double bond is, first thing is, you have a p orbital from oxygen interact with this sp2 hybridization orbital through head-to-head interaction. So this is the single bond, okay, formed by this carbon and oxygen atom. At the same time, you have a p orbital on carbon, p orbital on oxygen. These two orbitals will interact with each other through side-by-side interaction. So this is the pi bond. Okay. In other words, for this CO double bond, you have two lines. Can you see that? Okay, one line is sigma bond, the other line is going to be pi bond. Okay, that's pi bond. The line that represent pi bond means that these two areas above and below this CO pair. Okay, and that sigma bond is the this interaction between the CO atoms. All right, so this is the pi bond. Another example about the pi bond. And again, let's take a look at the sp2 hybridization. Well, when we talk about the hybridization mode or hybridization orbital of the central carbon atom, again, as you can see that central carbon atom, you have three bonds, two single bonds and one double bond. Remember, when you count electron groups, and we said electron groups means lone pair and chemical bonds. It doesn't matter whether the chemical bond is single bond or double bond. You always count one chemical bond as one electron groups. Okay? In other words, this double bond will be counted as one electron group. Therefore, for this central carbon atom, it still has three electron groups. That matches with our definition regarding the hybridization here, sp2 hybridization means 3 electron groups. So for carbon here, it is still sp2 hybridization. This example, for both carbon centers, okay, they have 3 electron groups, 2 single bonds, 1 double bond. And now when you talk about this double bond between 2 carbons, again, you see sigma bond and pi bond, okay? All right. And what happened here is you have 2 identical carbon atoms here. When they form the carbon double bond, okay, you have both carbons with sp2 hybridization, okay. And you can see the chlorine here. Of course, chlorine will have its p orbital intact with the hybridization orbital of the carbon through head-to-head interaction. So this one here, this single bond is sigma bond. This one, again, sigma bond. Single bond is always sigma bond. And a double bond, it includes 1 sigma bond and 1 pi bond, okay? So I expect you know how you label those bonding types, okay, based on its property here, okay. If that is a head-to-head interaction, sigma bond, okay. If that is the head-to-head interaction and pi interaction, then that's gonna side-by-side interaction. It's gonna be a sigma bond and pi bond, so that's gonna be a double bond. Now the next one is sp hybridization. Well, in this case, sp means you have 1 s orbital and 1 p orbital intact with each other, like this diagram shows you. Okay, so these 2 orbitals will hybrid to form 2 equivalent hybrid orbitals. Okay, and then when you have this electrons on this 2 hybrid orbitals intact with the surrounding atoms, you are going to have a molecules, most likely a central linear geometry. Okay, so this is a diagram, you know, before the hybridization, and this is a diagram, the sp hybridization orbital after hybridization. Okay, a good example about this sp hybridization is this molecule. You have a triple bond between the 2 carbon atoms, and you can see that when you have hydrogen interact with this central carbon through head-to-head interaction, this is going to be a single bond. Therefore, for this CH bond, it's going to be sigma bond. And same thing for this one, head-to-head interaction. So this is going to be sigma bond. And for triple bond, you have 2 sp hybrid orbitals interact each other through head-to-head interaction, the purple bubble in between. Okay, so that's gonna be the central line. I'm gonna write it here in the larger version. So you have triple bond, H. So this is sigma. This is a sigma. For this triple bond, the middle line here is gonna be sigma bond. Okay, as this purple bubble shows. Okay, and you would have 2 pi bonds. How is that? Because you have 2 p orbitals on the carbon, and those 2 p orbitals, because remember the 2 p orbitals, they are going to be, the bond angle would be 90 degrees, right? So you have 1 pi bond here, okay, and another pi bond here. Those 2 pi bonds are going to perpendicular to each other. So for the 2 lines on the 2 sides of the central sigma bond, it's going to be pi bond. Okay, so triple bond will give you 1 sigma bond and 2 pi bonds. And now let's take a look at the electron groups of this carbon atom. You have 1 single bond and 1 triple bond, 2 electron groups. Therefore, you know, that matches with the sp hybridization. Okay, so sp hybridization in this case. All right, now the next one is going to be SP3D hybridization. Well, let's take a look at this example. Arsenic with 5 fluorines, around it, And we say that this is an exception of the octet rule. The arsenic has 10 electrons. It's more than 8. So how do we explain this kind of interaction? Well, if you have the S and 3s and 3p orbitals to form hybridization orbital, then maximum you would have just 4 orbitals, right? And the maximum you would just have 8 electrons. Okay, so apparently that's not going to work for arsenic because it can accommodate 10 electrons. Then what should we do? Well, in this case, one of the d orbital will be involved. Okay, one of the 3d orbitals will be involved in the hybridization. In other words, one 3s orbital, 3p orbital, and one 3d orbital, they'll hybrid to form 5 equivalent orbitals. Those 5, the electrons from arsenic on this 5 equivalent orbitals will interact with the fluorine through arsenic fluorine bonds. Okay, so to form this kind of the trigonobipyramidal geometry. And how do we call it? We call it Sp3D hybridization. 1s orbital, 3p orbitals, 1d orbital. Okay, so that is how we call it. How do we identify whether a central atom has a Sp3D hybridization or not? You take a look at the electron groups. You have 5 electron groups, then that means you have 5 equivalent hybrid orbitals. Therefore, it's going to be Sp3D hybridization. Next slide is going to be Sp3D2 hybridization. Well, in this case, 1 s orbital, 3 p orbitals, 2 d orbitals will be involved to form 6 equivalent orbitals. To form this octahedral geometry, one good example is SF6, very heavy molecule. You have 6 identical SF bonds, and it's the sulfur again. It is an exception of octet rule because in this case sulfur has 12 electrons, so you have 2, 3, 1, total 6 orbitals involved. So maximum you can get 12 electrons on this 6 equivalent orbitals, right? So that's why sulfur can get more than 8. Anyway, so again, how do we identify whether a central atom is Sp3D2 hybridization or not? You take a look at the electron groups. 6 electron groups means 6 equivalent hybrid orbitals. That means Sp3D2 hybridization. Okay, so this is a summary about what we learned. Well, how do we identify? This table essentially tells us how we identify the hybridization of a central atom. Well, you take a look at the number of the electron groups. 2 means sp hybridization. 3 electron groups means sp2 hybridization. 4 electron groups, sp3. 5 sp3d. 6 sp3d2. All right. So in order to identify the hybridization of the central atom, you need to draw the loose structures properly, and that is pretty much the prerequisites for you to identify the hybridization of the central atom. Okay, so if you still don't know how to draw the loose structure, please review the videos in chapter 5, and we'll do practice when you come back to class. Okay. All right, folks, let me know if you have any questions.